So I'm proud to introduce our first lecturer. That's Yuri Makhlin, who is a professor at the Higher School of Economics in Moscow, and he's also working at the Landau Institute of Physics. Yuri is working on Josephson junction-based qubits since 2000, I think. So, and he knows a lot of how to build quantum logic from superconductors. And yeah, let's begin.
Thank you very much. Yeah, you see the topic of my lecture, which is should be called the basic introduction to quantum computing. And we agreed with the organizers that I will cover it, although you may consider this topic to be in fact off topic in terms of how it fits in this school, which is in the first place devoted to superconducting quantum devices. But in fact, it is not. The field of quantum computing, or more generally quantum information processing, is one of the fields where these devices are the field of application of these devices, and in fact, one of the major motivations behind the research in this field. We'll discuss basically today the topic of quantum computing from the point of view what kind of device do you have to claim that you have a quantum computer. As I said, this field also gives you a kind of a language or direction of thought, which allows you to ask questions in a sensible way, which is somewhat different from other approaches based on our experience, I don't know, in physics or engineering. Anyway, this turned out to be a very useful way and also interesting in itself. I will discuss at the beginning of my lecture the topic of requirements to realization of quantum computing, and then we'll touch upon the topic of superconducting qubits. This, of course, will continue and perhaps somewhat overlap with what has been discussed yesterday in the introductory lecture by Yuri Nazarov, I think. And I'm sure will be extended by at least some of my colleagues in the later lectures in this school. I will also discuss such questions briefly as decoherence and readout in these devices, by basically mentioning that they are important points here. If there is some extra time, I may touch upon some examples of quantum algorithms, but that's a side topic anyway. So let's move on. Quantum computers. Let me just remind you very briefly to set the stage what quantum computers are. Standard, or we'll say classical computers, are built of elementary blocks which are bits to state systems. In the quantum case, the memory of a quantum computer is built out of elementary blocks which are two-level quantum systems, or quantum bits, qubits in short. And unlike the classical ones, they can be not only in the state, in two possible states, 0 and 1, we call them, but as we know from quantum mechanics, also any superposition of 0 and 1, as shown here. If you have one or many qubits, a quantum computer memory, its evolution in time is governed by, in quantum mechanics, by the Schrödinger equation, and the evolution is unitary, as you see here. You still can see my mouse, I hope.
We see your mouse.
Okay, very good. And in the simplest case, when the Hamiltonian of the system H is does not change in time, the evolution operator is given just by the standard exponent, the solution of the Schrödinger equation, when the Hamiltonian does change in time, as will be the case which we have in mind, we also know how to solve it in principle, at least. And from this point of view, quantum algorithms are just global unitary transformations of the quantum state of our many qubit system, of our quantum computer memory. And of course, as always in the field of information theory, in quantum information theory, we assume that the quantum algorithms are built out of or are decomposed in terms of elementary quantum operations or quantum logic gates, which influence only a small number of qubits, let's say 1, 2, 3 qubits. And we build quantum algorithms out of these elementary operations, which is the concept which is familiar to us anyway. Before moving on, why do we consider the quantum information processing at all? Well, there are motivations on the side of computations or information science. One reason, which was much cited at the beginning, was the constant miniaturization of elementary blocks of the hardware in computers, so that we would have to take into account quantum effects in these devices. But also at the early stage, already at the beginning of the 80s in the last century, the potentially greater computational power of such devices was cited and advocated, for example, or mostly in the first stage by Richard Feynman or David Deutsch. Nowadays, I think that goes under the name of quantum supremacy, and it's very much related to that. On the other hand, on the side of research in physics, the research into realization of quantum computers touches upon many fundamental questions in quantum physics of various physical systems. And from the point of view of designing new devices, there are also very many new interesting questions that as you know and learn in this school anyway. A major boost to this field was given by the invention and the discovery by Peter Shor of the famous Shor algorithm for factorization of large integers. He has shown that unlike on a standard computer, this can be done only in time which scales polynomially with the size of the number of the integer which we want to factorize, that is with the number of digits. Just a couple of words about possible applications. The major application is, of course, just quantum computation. And I should mention here that the first known, at least to me, and I think to many of us, the mention of the potentially greater computational power of quantum devices as compared to the classical devices was given by the famous Russian mathematician Yuri in one of his books, I think already in the end of the 70s. Other possible applications have to do with the transmission of quantum information. This is the field of quantum communication, where people discuss how you can transfer quantum states. And you have heard perhaps of the notions of quantum teleportation in particular. Another or related topic is quantum cryptography, where you discuss the use of quantum channels to reliably transfer information, quantum information, or in fact classical information as well. And I want to mention also the thing which was featured on the previous slide too, the use of quantum devices for the simulation of quantum systems. It was, in fact, when Richard Feynman advocated this point, and what he had in mind that if you want to simulate a complicated quantum system, it's the quantum dynamics, the evolution due to the Schrödinger equation. Possible quantum devices are much more suitable for this purpose because they are quantum by themselves. They are governed by the Schrödinger equation. And he, in fact, not only on this metaphysical level, but he also gave an example of how the system of many particle systems, whose Hamiltonian is a combination of the kinetic energy of the particles and the potential energy of the interaction, how it can be simulated efficiently on a possible quantum computer. Very good. There are also other points which are other applications which are close to quantum devices, which I don't want to go much into detail of. Before discussing the actual topic of realization or requirements to realizations of quantum computers, let me just set the stage by introducing some notation. Quantum operations, as we said, are unitary operations. In the simplest case, when you have only one qubit is a two-level quantum system. So any unitary operation on a single qubit can be described by a 2x2 matrix if we fix some basis. Let's call the basis states 0 and 1, as it is shown in the upper expression. This is the standard computational notation. If we consider, for instance, an unitary operator given by this 2x2 matrix, 0, 1, 1, 0, what does it do to the quantum states when it is applied? It exchanges, in fact, two basis states. It transforms 0 to 1 and 1 to 0. In this sense, it is nothing but a NOT operator. However, unlike in the classical case, it can also be applied to any superposition of 0 and 1. And then it gives, you can say, the same superposition of 1 and 0. A little more quantum example is the square root of this matrix, which is given in the next line, the square root NOT operator, which is given by this matrix, and it is shown here how does it act on 0 and 1. What is interesting, an interesting property of this operator is that when you apply it twice, you get the same result as the result of the NOT operator. So this is shown as a product of two operations. Square root NOT times square root NOT is not. And of course, it's easy to see that a square root NOT, so to say, exchanges 0 and 1 halfway, and there is no analog of that for a classical bit. Another example of a non-trivial single qubit operation is below the phase shift operator, which is diagonal in our computational basis. It does not exchange 0 and 1. It leaves 0 as is, and it also leaves 1 as is up to a phase factor. It multiplies one of the two states by a phase factor, or we can say that what's important, it changes the relative phase between the two states. So these are examples, in fact, relatively, in some sense, complete sense of examples of operations of single qubits. But anyway, another point which I want to bring up now is the notation. It is always, or it is often useful to, and it is often done, that the qubits are thought of as analogs of spin systems, basically because a two-level quantum system, one example of it is a spin 1/2 particle. And you can use the same notation, the same language as for spin 1/2 particle. So we often will denote the state 0 as a spin up state and the state 1 as spin down state. Just a second. Yeah, so any wave function of a two-level system, which is a superposition of the basis states, can be parameterized in this way, which is shown here by two angles, theta and phi, which can be thought of, in fact, as the coordinates of a point on the unit sphere, which is shown in the picture. The sphere in this context is always often referred to as a Bloch sphere. And in terms of this, in these notations, we can, well, since we are discussing a spin particle, we can try to ask us what is the operator of the spin. It has three components, a vector operator, and we know from quantum mechanics that for a spin half particle, It can be expressed in terms of the three Pauli matrices. Let me briefly go to the next slide. These are the well-known Pauli matrices known from quantum mechanics of spins. Some fixed matrices sigma x, sigma y, and sigma z. So this is the vector of the spin operator, which is sometimes called, or in this context, the pseudo spin, because we do not necessarily have a real spin, just a two-level system, but formally they're equivalent. Now, if taking this wave function, we calculate the average value of the spin operator of the vector of three sigma matrices, we get some vector n, which in this case is a unit vector, is the same point on the unit sphere, which is shown in the picture. It is characterized by the spherical angles theta and phi. In fact, this consideration can be extended to situations when our qubit is not alone, when it interacts with the rest of the world, or we should say entangled with the rest of the world. We'll discuss this notion. If you don't know it, the quantum entanglement, discuss it later. In that case, as you know from quantum mechanics, the qubit does not necessarily have a wave function of its own, but its state can be described by the so-called density matrix. But anyway, the average value of the spin fully characterizes the quantum state of this two-level system, even in that case, except the average value of the spin is not a unit vector anymore. It's vector of the length, which is smaller than 1. So in that case, the red point is not on the sphere, but inside the sphere, you can say in the Bloch ball. Good. Now, if we are to consider the dynamics of our qubit, then we have some Hamiltonian, which describes its dynamics. Well, first in the case when it is decoupled from the rest of the world. The Hamiltonian is a 2x2 matrix, which can always, obviously, because it's Hermitian, can be written in this way. And if I rewrite it in terms of the Pauli matrices, I have this notation. The first contribution B0 is irrelevant. It's just a constant, which doesn't change the state anyway. So basically, my Hamiltonian is equivalent to the Hamiltonian of a spin in an external magnetic field, or one can say pseudo spin in a pseudo magnetic field. So the physics of qubits in this sense is very much similar to the physics of spins in, or a single qubit of a spin in a magnetic field. And this language, as I said, is often used. If we want to describe the dynamics and write down the equation of motion for the spin operator using the standard expressions known from quantum mechanics, calculate the commutator, we can find out the dynamics of the state, which can be described by the dynamics of the unit vector n, is given by this expression in the green box down here, which is basically the precession, or you can say alarm precession of the spin around the direction of the magnetic field. That's a useful way to think about the dynamics. And a couple of examples of the single spin rotations or single spin operations, quantum gates, if you wish. If our Hamiltonian is proportional to sigma x, or you can say that if the pseudomagnetic field is in the x direction, then we can pick the angle of rotation or the strength of the field such that the rotation is around the x-axis, as shown in the picture. And then if the angle of rotation is pi, you get this operation, which is nothing but the same knot operator, which we have seen already. If you take the language, the angle half of that, pi over 2, you would get a square root of naught. Now, another example is a rotation around the z-axis. In this case, the trivial calculation tells us that if the magnetic field is in the z direction, what we get is a phase shift operator, the relative shift of the phase between the two states. And another example, which will be featured later on, is the so-called, sorry, there is a misprint. It's an Adamar gate called after a French mathematician. atomar, it's equivalent to a rotation of the spin space around some direction, which is in fact x plus z. Anyway, it's this specific 2x2 matrix. It's also a single qubit gate. So this is how it works in the simplest examples, but let's now move on and discuss the question of what kind of a device and functionality of our device we should have to be able to perform quantum computation. There are, in fact, a number of ways to think about quantum computation. I use the standard or the simplest way, the so-called circuit approach to quantum computation, which consists in thinking about quantum algorithms as a combination of elementary gates. Anyway, let's move on. These requirements, or as they say, criteria of which quantum computers need to satisfy, were formulated in this way by David DiVincenzo more than 20 years ago. That was at the early stage when it was important to tell to the physics community what actually is expected from them in terms of research in their various quantum systems. There are, he has formulated that as 5 criteria, or which are often referred to as DiVincenzo criteria. And the first point here is that you have to have qubits. You have to have your large quantum computer as a combination of a number of, to some extent, independent initially elementary building blocks, 2-level quantum systems. We have mentioned that already. They could be realized physically in a number of ways. Here are the simplest examples. Indeed, spin half particles, or 2 polarization states of a photon, or internal levels of an atom. They have to have well-defined Hamiltonian, and in the ideal case, if we consider a qubit, we should have it always, or basically within these 2-level subspace. It could have higher levels, any physical system, the 3rd or 4th level, but the leakage to this state should be, in the ideal case, there should be no leakage, but of course, in reality, there could be some, but it should be minimized. And finally, whatever we do should be scalable in the sense that we should be able to take any number n of qubits, depending on our problem at hand, which we want to solve using quantum algorithms of our computer. So it's not a fixed device with, I don't know, 17 qubits or something. We should be able, at least in principle, to build a similar device with any number of qubits. Now let's move on and discuss what can we do with these qubits. What should we be able to do? And the first thing is single qubit logic gates. I will discuss this in terms of writing down term by term the Hamiltonian of my system. And the first term here, which is shown up there, is this one, which tells us that each of our n qubits or n spins is coupled to its local external magnetic field, H sub I of t. Of course, we assume that these local fields should be under control. We should be able to switch them on or off and control their strength ideally. So what happens when all these fields are switched off? When the Hamiltonian is 0 and there is no dynamics, the quantum state is preserved. If we switch on a local field for one of the qubits, for instance, in the x direction, then we called then we have what is called here a spin rotation or a spin flip. If in this case we have a rotation in terms of the Bloch sphere, we have a rotation about the x-axis. The angle of this rotation can be easily calculated. Here it is shown in terms of the unitary operation. The angle alpha is controlled by the strength of the field and the time span of the operation by the product h time tau. So we have this kind of operation, which includes, as we have seen, the knot operation and the square root knot as particular examples for some values of alpha. Another possibility is to switch on field in some other direction. Let's look at the z direction. In this case, as we have mentioned already, the operation which we achieve is diagonal, described by a diagonal matrix in the computational basis, and it introduces a phase shift between spin up and spin down states. Again, the angle of this phase shift is controlled by the strength of the field and the time span of the operation. And in terms of the Bloch sphere, it's a rotation about the z-axis. It's easy to understand that it is sufficient to have these two kinds of rotations about, say, the x and z-axis about any two directions, in fact. And it's easy to understand. We know, for instance, from mechanics that any rotation can be decomposed in terms of Euler angles into rotations about x and z directions, for instance. Very good. That was about single qubit logic gates. And here are the examples which we have discussed already. The next step is to move on and make the qubits interact. Without them, we have separate qubits, and each of them can be rotated in principle, but of course, it's not enough for joint dynamics of our quantum computer. To have the qubits live together.
Okay, if you're not hearing Yuri, I'm not hearing him either, so probably there's some connection problem right now. We'll see if it solves it by itself. If it doesn't, then probably we'll ask him to reconnect.
Yeah, can you hear now?
Yes, we can hear you. We don't see your slides anymore, so you'll have to start them again.
Yeah, I have, I guess, to share the desktop.
Yep.
When have I been interrupted?
Yes, on this slide. So we didn't get to the 2 qubit gates yet.
Right. So I started to talk about the necessity to make them interact. And we introduce, in fact, should have at least some interaction between the qubits. In this example, between any pair of qubits I and j, but this can be relaxed a little bit, of course. What's important is not the metric structure of this interaction, but the fact that the strength of the interaction should be controlled. We should be able, ideally, to switch it off. Then there is no interaction, and the qubits can be controlled one by one. And when we switch on the interaction J capital, then we couple the qubits and they evolve together. For instance, if the coupling between qubits number I and j is the only on term in this Hamiltonian, all the other terms are switched off, then the Hamiltonian is given by this expression in the middle of the slide. And if we wait for some time tau, then we can calculate using the Schrödinger equation the exponent of this Hamiltonian, and we end up with this 4x4 matrix, 4x4 because we have now it acts on 2 qubits, and it is 2x2 or 4-dimensional Hilbert space. This is the one of the standard bases, the computational basis in this space. So in this basis, the matrix looks like that. And the angle gamma here is again controlled by the strength and the time span of the interaction in this case. These interactions between qubits, they bring up the 2 qubit gates, and 2 qubit gates, they, in particular, what they give us is the possibility to correlate or entangle the qubits. Here, I should remind you the notion of quantum entanglement, which appears when you discuss 2 quantum systems, for instance, 2 qubits or 2 subsystems of your system. In this case, the wave function of the total system A plus B may have different properties. One situation is when A and B are independent, or mathematically, this is the case when the total wave function is the product, or mathematically, a tensor product of the wave functions of A and B. This is called the product state, and this state is called, or in fact, is non-entangled. They are independent in terms of the statistically independent. Examples of these states are shown here in the middle. The simplest example is the when both qubits are up, or one up and the other down. But the further line, where you have a combination of 4 different terms is also a product state, as you can easily see by opening the parentheses on the right. The examples of states which are not products, the so-called entangled states, and that's most of the states, in fact, are shown down here. You can call them a triplet state and a single state. Well, there is no proper normalization, but that's trivial. So the situation when the state is not a product state is called quantum entanglement, and you can easily see that in this case you have correlation of properties between the 2 qubits, and that's coming back to the 2 qubit gates. That's what 2 qubit operations give us. For instance, with this specific operation, which is shown by this matrix, if you start, for instance, with the state shown down here, up, down, and pick up this specific angle, you end up with this kind of state, which is obviously an entangled state. It's not a product state. But anyway, quantum entanglement seems to be a very important resource as far as quantum information processing is concerned. That's why I mentioned it a few times. So altogether, what we see is that we need to be able to perform single qubit gates and 2 qubit gates. And this is summarized in this picture, which basically tells you how the evolution during the quantum algorithm takes place. So the time goes from left to right in this picture. Each line corresponds to a single qubit or a single spin. You see errors, spin errors, and this for these particles on the left. As time goes on, we apply sometimes single qubit gates, sometimes 2 qubit gates to some pairs of qubits. Sometimes they are, of course, applied in parallel. And at the end of the computation on the right side, all or some at least of the qubits should be measured, and this is illustrated here with the Stern-Gerlach magnet. What is important, this statement about the universality of the set of 2 qubit and single qubit operations. It's not obvious, but if you formulate it, it's quite easy to check it for mathematically, for instance, in terms of, I don't know, Lie algebra theory. The statement is the following: if you are able to perform on any of your qubits a full set of single qubit operations, and then you are able to perform on pairs of qubits some non-trivial 2 qubit operation, and often they say the so-called C0 operation, but in fact almost arbitrary 2 qubit gate is sufficient. So if you can do this by a combination of these gates, single qubit and 2 qubits, you can achieve arbitrary operation on the whole quantum computer, on the set of all qubits. This is statement is called a single bit, or always referred to by saying that single qubit and 2 qubit gates form a universal set. You don't have to have any other elementary operations. It is sufficient to be able to perform these. Very good. Just an example of quantum algorithm, how these single and 2 qubit gates can be used to build out something useful, or at least seemingly useful. This is an example of the algorithm of the so-called discrete Fourier transform, or in fact a quantum version of it. To introduce it, let me first introduce these the basic elementary gates. The atomar gate, which I've mentioned already, and which will be indicated by this square with one input from the left and one output line on the right. It implies that we apply it to a single qubit, and of course get the to initial state of a qubit, and then at the output we have the final state of the qubit. I remind you that it's given by some specific 2x2 matrix. And another gate, which is shown on the right, a 2 qubit gate. It has 2 inputs on the left and 2 output lines on the right. In the standard computational basis, it is given by this specific matrix, which is diagonal and has units on the diagonal except the non-trivial phase factor e to the I phi in the lower right corner. So all states, basic states, remain intact except for the down-down state, which requires an extra phase factor. And this phase factor phi is a parameter of this circuit, of this gate, 2 qubit gate. The way it is drawn in the picture reminds us that this gate, in fact, can be described equivalently by saying that it is a rotation by angle phi about the z-axis of the second qubit conditioned on the state of the first qubit, which is to say, if the first qubit is in the state 1, there is a rotation of the second qubit. If the first qubit is in the state 0, there is no rotation. So this situation is referred to as a controlled phase shift. Anyway, so we have these specific gates, single qubit and 2 qubit gates, and then out of them we build the following algorithm shown in the picture. This specific example is for 4 qubits numbered 0, 1, 2, and 3. Each line corresponds to 1 qubit, and as time goes on from left to right, we apply a single qubit gate, then a 2 qubit gate to the qubits, to the lower 2 qubits, then again a single qubit Adamar to the qubit number 2, and so on. The structure of this algorithm is also obvious, and it's easy to understand how it scales with the number of qubits. In the following sense, you can think of it as this specific picture is consisting of 4 blocks. The first block is just the single Adamar, then this triangle, if you wish, the 2 gates applied to the qubits 2 and 3, then the larger triangle, the 3 gates applied to the lower 3 qubits, then the largest triangle, the 4 gates applied to all the 4 qubits together. So it's easy to understand how to scale it up to a larger number of qubits. But the question is, what does this, of course, the combination of all these elementary unitary operations is some unitary operation on the whole space of 4 qubits, but what does it do? In which sense, why do we call it a Fourier transform? Well, to formulate it, let me introduce another notation for the basis. In this space, we have 4 qubits, so 2 states for each 2 times 2 times 2 times 2 is 16 states. In the case of n qubits, we can have 2 to the n states, which can be denoted by binary strings. The first string corresponds to the state of all qubits 0, then the second state is all qubits in the state 0 except the last one, which is in the state 1, and so on. The same states can be denoted just, of course, by integer numbers from 0 to 2 to the n minus 1. So 2 to the n possible states. So in this sense, any input state which we can feed to this algorithm as the initial state is a superposition of these numbers between 0 and 2 to the L. This is the initial state for our discrete Fourier transform algorithm. And also the output state is a linear superposition of the same integers, or the states numbered by integers between 0 and 2 to the L minus 1. The claim is that the coefficients in the superpositions, the output and the input, are related to each other by the expression down here at the bottom of the slide, which is nothing but the Fourier transform. Well, of course, the discrete version of the Fourier transform. One can mention here the evaluate the how many steps does it take to do this operation. Obviously, it's easy to understand that the number of steps scales quadratically with the number of qubits. While for, well, it's not completely fair comparison, but still, if you consider the best classical algorithm, the fast Fourier transform or various variations, the time they take scales exponentially with the number of qubits. I stress that with the number of qubits, or in other words, with the number of digits in the number. So in this sense, the quantum algorithm is much faster, although it solves a slightly different problem, but anyhow. By the way, I've mentioned the phases of rotations, which are shown here in each square. And they are different for different operations, and the exact values depends on the numbers of qubits I and j, and shown are to the right of the picture, this green phase phi ij. Good. So if you have any questions, then go ahead and ask them during the discussion, of course. Very good. So what we have discussed so far was that we need to analyze a quantum computer, we need to have qubits and need to be able to perform quantum operations. Single qubit, we say logic gates with logic gates with single qubits and with pairs of qubits. That's sufficient for the purposes of changing the state. However, we need I have to mention more points. I mentioned that there are 5 criteria, but the other criteria are somewhat simpler, or not really simpler, but I will not dwell much on that. So the next thing which we have to mention is the preparation of the initial state. When we apply our gates, we need to start from some well-defined initial state. In this, in the circuit quantum computation, we assume that the initial state is simple and the complexity is in the algorithm itself, in the sequence of the gates. We assume that we, for instance, want to prepare the states, all the qubits in the state 0, or all the spins in the state up. For most realizations, but not for all, but for most of them, it's not a problem. And this is achieved by decoupling all the qubits, for instance, from each other, and by cooling the system down to its ground state, just by waiting, or by measuring each of the qubits. That's, if you think about quantum measurement, that more or less gives you the same result. All the qubits are in well-defined state, and not necessarily 0, but then if it is 1 for some of the qubits, you can flip them. Anyhow, initialization is a simple step, for at least for us today. Another point is this green one, and to discuss it, we should realize that our ideal quantum computer, of course, is decoupled from the rest of the world, but the coupling to the rest of the world is unavoidable. You can think of it by saying that there are various noise sources which affect the dynamics of your qubit. And then it is not described anymore by a well-defined wave function of our system. It entangles with the rest of the world. And you can say that its quantum properties as a separate system degrade as time goes on. So in this sense, the coupling to the rest of the world, which is indicated by the last green term in the Hamiltonian, should be kept as weak as possible. So this degradation is as slow as possible. I will perhaps say a couple of more words later on about this point, but what is important here, and this is an important breakthrough in this field, is the concept of quantum error correction, which is the following statement. Naively, from the discussion we just have, it seems that as the time goes on, the quantum state degrades, and after a certain time scale, which depends, of course, on your system, but there is some typical time scale usually, which is called the dephasing time, and which is indicated as tau phi here. After a certain time, your system is not quantum anymore. It behaves more or less as a classical system, as one can understand. Naively, one would think that after this time scale, you cannot use any quantum properties of your system. There is no, so to say, quantum supremacy anymore. So naively, you think that the operation time of a quantum computer is limited by this time scale. And although if you are very careful and you know how to design your hardware, your quantum hardware, you can make this time sufficiently long, and that's an important point, of course. But always there is some time scale tau, and since quantum supremacy, quantum algorithms are in fact interesting when they are applied to large systems with many qubits, and which take a long time, which scales at least polynomially with the size of the input in your problem. Typically, it would tell us that the size of the problems which can be solved with a quantum computer is very much limited. And these devices, for this reason, appear to be useless, or at least not as useful as we would initially think. The point of the quantum error correction theory or quantum error correction discovery is that it's not completely true. There is a certain limit, a certain threshold, but if your decoherence time, this degrading time, tau phi is not infinite, but not too short. For instance, it's longer than some number. In this case, it's shown that 10,000 of the elementary operation times. Then you can show that you can perform quantum computation as long as you wish. But of course, you would need to interrupt your quantum algorithm and do special, you can say, quantum software special gates, which would compensate for the errors which are due to the external noise. So it's hard to discuss it in more detail at this point, but that's an important breakthrough in this field due to also Peter Shor and Andrew Steen and other godfathers. Good. And the last point, which I want to mention, the criterion number 5, is the fact that you need to perform the readout, of course, the final result, at least, of our quantum computation. And for this reason, we need we know to perform a measurement, which in this case is a quantum measurement, some non-trivial operation, which we should be able to implement. In terms of the Hamiltonian and the expression up there, it is shown by the the penultimate red term H measurement. It describes the coupling of our qubits to, or one qubit at least, to some kind of quantum detector measurement device, which we switch on when we want to perform the measurement and switch off when we don't want to perform the measurement, the ideal situation at least. Very good. So this picture summarizes what we want to have in principle to realize a quantum computer. And that's a simple or basic way to think about it, or at least one of the ways. Before moving on to some specific, basic but still realizations, I will discuss a couple of simple superconducting qubits. Let me also mention the field of quantum algorithms and ask the question why this can be useful, why the quantum nature of the hardware can be useful in terms of the computational power. This is sometimes discussed in terms of the concept of quantum parallelism. Let's imagine that we have some quantum algorithm. Let's say some algorithm, the calculation of the values of a function. If we think about the input state as one of the 2 to the n input state of the n bits, then in the classical case, to calculate the value of some function for each of the inputs, we would need to run the algorithm 2 to the n times for each of the inputs. In the quantum case, we can cheat. If there is a quantum algorithm which implements the calculation of the same function, so to say, we can, as the input state, we can use not each of the basis states, but a superposition of all of them. And it is shown in this expression on the right side. Well, in fact, in this case, it is shown due to the unitarity, we need to have 2 registers. The first register is the superposition of all the possible states, and the second register initially is 0. And finally, for each of the states, it contains the state which is has the number f of x. F is our function. So it contains the values of the function in this sense for all the input states at the same time. So in the quantum case, after a single run, we have 2 to the n values of the function at the same time. So in this sense, it's obvious that the notion of quantum supremacy is clear. The fact that we have the exponential speed up is trivial. But of course, there is some cheating. We know that it's not true that quantum computers can solve all the problems exponentially faster than the classical ones. In fact, it is very hard to find examples where it is so. And the resolution of this paradox in this case is, of course, in the fact that we to read out the values of the function, we need to perform the measurement of the final state. And we know that the quantum measurement, it would give you one of the values each time. It would collapse the rest of the wave function. So in this sense, after this computation and the measurement, we would always get only one value of the function, only for some x, which is unpredictable, by the way, but which x we would, f of x for which x we would get. But anyhow, so in this sense, if you want to get all the exponentially many 2 to the n values of the function, we need to repeat this algorithm at least 2 to the n times, of course. In this now tells us that, well, we are back to the square one. There is no speed up at all. Again, the resolution of this opposite paradox is that sometimes what we need to calculate is not the value of the function for all the input values, but some combination of those. One example is the Shor factorization algorithm, where we need to what we need to calculate is the period of the function, not the values of the function, but it is periodic, and we need to calculate the period, which would give us, in a simple way, would give us the factors. So there are cases, and Shor's algorithm is one example, where we can process this state, this superposition which we got of all x and f at x before the measurement, process them all together to get one quantity, not to the 2 to the n quantity, but one quantity which we need, and which contains in itself some combination of all these 2 to the n values. Then we have only one quantity, and we need to measure only one quantity, or a small number of them even, but let's think about one. And in this case, if we know how to deal with that, we can have a situation, or we can imagine a situation where we have exponential speed up and quantum supremacy. So that's a very bird's view on how quantum parallelism can help, or is able to help us sometimes, but of course not always. Well, very good. So that was an introductory discussion of the physical requirements or criteria to the realizations of quantum hardware, which is to serve as a quantum computer. If you have any questions at this stage, please go ahead and ask. What I plan to do next is to discuss briefly discuss some physical systems which implement this criteria. Good. But so if you come up with some questions.
There's a question from Ranjan Singh in the chat. So the first question is, what kind of impacts may be on quantum computation operations if the value of entanglement is weak or strong? Maybe I should repeat that.
Yeah, so I understand the question is, what is the role of entanglement in all this business? What happens if we have only weakly entangled qubits or strongly entangled qubits, right?
Yes, at least that's how I understand it.
Right. Well, it's an important question, of course. In physics terms, you can say ask yourself what happens if your interaction between the qubits is weak and takes only a short time when the only weak entanglement is affected, and what happens when it is strong. It's very hard to answer it in full generality. Of course, we understand that in the limit when there is no entanglement, there is nothing useful. All the qubits are separate, and nothing interesting, no many-body dynamics, no quantum computing can take place. Now, the degree of entanglement in general, of course, it grows in time. Of course, I mean, when you ask this question, you understand that. But anyway, I mention it. So if you perform more and more 2-qubit gates or few qubit gates, we entangle the qubits in our system stronger and stronger. What we can ask is the following question. If I consider a single 2-qubit operation, it can entangle two qubits strongly or weakly. This is a notion which can be defined, and you can define the degree of entanglement due to a two-qubit gate. So if our two-qubit gates are only weakly entangling, then it's clear that to implement the same quantum algorithm, we would need more steps. To achieve, you can say, the same degree of entanglement, you would need more weakly entangling gates. Then we would have to have strongly entangling gates. There are gates which are so-called perfect entanglers. We have the maximal degree of which bring the maximal degree of entanglement, and the one of the gates which I mentioned, the controlled node, the C node gate, is an example. But there are there are a number of those. So from this point of view, the stronger entangling gates, or the gates with the maximal degree of entanglement, allow you to perform algorithms in a more efficient way. The weaker the entanglement per gate, the more steps you would need. I don't know if all these answers exactly what you have asked, but at least there is this series of questions which can be discussed in this connection.
Okay. Judging from the fact that Ranjit Singh thanks you for the answer, that probably answers his first question. And the second question is, how did you derive the number for coherence time? I think he's referring to the slide where you mentioned that the phase time is 10 to the 4 of the operation time.
Right. Well, I'll perhaps say a couple of words about that at the end, but basically, let me come back here. So one way to think about it is the following. If in this picture, A is my quantum computer or a qubit, and B is the environment, when they are decoupled, the wave function is a product. It's shown here. If they are coupled, the wave function deviates from the product, and deviation is stronger and stronger with time. In the typical situations, you can show that the deviation grows exponentially. And the time scale in this exponent is exactly the time scale of this dephasing or decoherence time scale. So this is on a very metaphysical level. But basically, you can say the deviation of your the state of your system, in fact, the density matrix of your system, of your single qubit or many qubit system, from the ideal due to the coupling of the environment typically grows exponentially with time. Not always, it depends on the properties of the environment and the coupling, but the typical situation is such, and it is always often characterized by a single time scale. So it's, I don't know, to discuss it in more detail, I would need a longer time. I will say again, as I said, 2 words at the end of the lecture, I hope. Thank you, Leah. If there are more questions or more questions appear in the chat, please tell me.
No more questions for now.
Yeah,
so
good.
Let's move on.
Because I do not keep an eye on it. Good. So realizations. I will mention. I will mostly discuss of course, the superconducting realizations. But let me mention some other possibilities. Just briefly mention. No real discussion of them. Some realizations which were studied from the very beginning and have some perspective. One is based on ions trapped in special traps. If you is shown in the picture, they typically form a chain, and each ion serves as a qubit with in the simplest case, 2 internal states of each ion, 2 states of the electrons in the ion, serving as 2 computational states. And the ions are coupled to each other, and this coupling together with the laser excitation from outside can be used to process quantum information in this case. Another example in the lower part of the picture uses the nuclear spins in the context of nuclear magnetic resonance experiments, nuclear spins in some complicated molecules. which can be addressed individually. Well, that's a memory body system, so there are many molecules, but there are identical spins in each of them, so you address all of them simultaneously. Without going into any detail, let me mention that one of the problems initially in this field was the fact that it's hard to, in fact, initialize the state. Ideally, because the typical temperature here is typically not low compared to the energy scales of the fields which you can apply. But what I want to mention that exactly in this context, some simple initial demonstrations of quantum algorithms were done, and this is the system where I think about 20 years ago the short factorization algorithm was run for the first time, and it was shown that 15 is 5 times 3. It was verified using this hardware. Well, anyhow. Other examples include solid state devices. Here, another example of what is called now as the spin qubits, which use the spin degree of freedom of electrons in, for instance, in semiconducting heterostructures. And this is an advanced field. But without spending much time on it, let me move on to the topic of superconducting qubits, or which are often referred to as Josephson qubits or quantum bits, because the basic element here is a Josephson junction. So these are electric circuits which also contain Josephson junctions, which I'm sure you have discussed at least yesterday, if you don't even haven't heard about that before. So the Josephson junctions are nonlinear elements in these electronic circuits. But anyhow, so why the superconducting systems or superconducting electronic, nano-electronic circuits could be interesting at all? Why do they have a potential for realization of quantum hardware? Well, they, on one hand, they have the intrinsic coherence of the superconducting state, which allows them or give them potential to be coherent for a long time. That's an important point. And they combine it with the techniques developed in this field, in the fields of electronics or nanoelectronics. These, on one hand, the single charge electronics or single electronics, if you wish. And on the other hand, the field of superconducting quantum interference devices, the SQUIDs. So this combination turns out to be quite useful and promising. What is used as a quantum degree of freedom in these devices is either the charge on some superconducting islands or the phase degree of freedom, for instance, the drop of the phase of the superconducting order parameter on Josephson junctions. You've discussed these notions yesterday in the lecture on quantum mechanics of these systems. Some properties of the systems relevant for our discussion are shown in the lower part of the slide. First, I need to mention that these degrees of freedom are macroscopic. Well, this is the charge, well, of not huge, but still a macroscopic system, which can contain, I don't know, tens of thousands, or depending on the size of the superconducting islands we are talking about, tens of thousands of electrons. And the phase degree of freedom, the phase of the superconducting order parameter, is of course a macroscopic quantity. So this should be contrasted with the microscopic degrees of freedom of internal levels, so in atoms or ions, or the spins of nuclei, or the polarization states of photons and other possible realization of qubits. The notion of macroscopic quantum physics and macroscopic quantum effects, and the idea to test it with superconducting devices, Josephson junction devices, was developed and advocated by Tony Leggett in the beginning of the 1980s. And in fact, there were even some experiments at the time, but the without much success, though, well, with some success, but let's say I will mention the notion of macroscopic quantum coherence, which was in fact observed or demonstrated only later on when with a new motivation from the field of quantum computation. Another property of Josephson quantum bits, which needs to be mentioned, is that these systems are artificial. They are often referred to as artificial atoms. They are designed and fabricated. Of course, you can say that there is a drawback of these systems because they are never identical, unlike real atoms or unlike ideal qubits. But at the same time, they give you the advantage in that you can control the properties of the systems during design and fabrication. Again, due to the developed techniques, the question of scalability, or the problem of scalability in this case, it means scalability to the larger number of qubits, is somewhat simpler in this field, or in fact, in solid state devices more generally, and in superconducting qubits in particular, because of the developed fabrication techniques. Of course, it doesn't mean it's trivial, of course. I don't want to tell that to my experimental colleagues. But if you know what to do, what you want to do in principle, it's easier typically to scale it up as compared to quite a number of microscopic realizations. And finally, we understand that the systems we are talking about are nano-electronic circuits. They are electronic by themselves, and it's easy to integrate them in electronic circuitry for control of their dynamics and for the readout. Well, that's very general discussion, but let's look at them more specifically. I will start from the so-called charge qubits. I perhaps don't discuss what is a Josephson junction. You've seen that already. In the charge qubits, we are discussing very small devices, and the important energy scale here, let me mention only that, is the so-called charging energy, which tells us by how much the energy of some capacitors change when you add a single electron to it. This is the charge of the electron squared divided by twice the capacitance. This energy scale should be large. Typically, well, in some cases, the largest energy scale in our system. It defines its basic properties. Let me mention some simple systems which will show you how the simplest qubit can work. But let's start from not a superconducting, but a normal state, a system made of a normal metal, the so-called single electron box. This box is the square in the picture in the middle with the number n in it. And it is coupled by a tunnel barrier, this blue one, to the upper electrode, and also voltage biased through a gate capacitor, C gate. Now, if I think about the system as a system of two capacitors, the gate capacitor and also the effective capacitance of the junction, of the Josephson junction, Cj, I can calculate its electrostatic or charging energy as a function of the applied voltage and also the function of the charge on the middle island. By the way, the charge on this island, how can it change? It changes only by, in the ideal case, of course, changes only by tunneling of electrons via the tunnel barrier. And in this sense, it can be thought of as an integer number of electron charges, as shown in the picture. So if we calculate the energy, we'll get the expression which is shown to the left. We have the total capacitance of the island in the denominator, and we have an expression in the numerator which is quadratic in terms of the charge and the voltage applied, as one could expect, of course, from electrostatic energy of these capacitors. If I plot this energy as a function of the applied voltage, the gate voltage Vx, for different numbers n of electrons on the island, I'll get a set of parabolas shown in the picture. So when we have 0 electrons on the island, the charge Q is 0. We have the leftmost parabola. If there is 1 electron, we have the next parabola, and so on. Now, if I change gradually my voltage in this picture from left to right, and ask myself at each value of the voltage, what is the lowest energy state? Then I see that initially around 0, this is this, well, I will get this green line. Initially, this is the line corresponding to the charge 0, then to the charge, it switches to the charge E, then to the charge 2E, to the charge 3A, and so on. If I plot this charge as a function of the voltage, the charge in the lowest energy state or the ground state of the system, you will get this line, this staircase, which is often called the Coulomb staircase. Now, what changes in the superconducting state? You have the same picture, but now we have a superconducting device. And the one thing which changes is that the major mechanism of changing the charge is we assume is the Josephson effect, the coherent tunneling of Cooper pairs via the tunnel barrier. And if it were the only effect of changing the charge would be quantized as terms of the charge of the Cooper pairs, 2e. So it would be an even number 2n times the electron charge. And however, sometimes also single electrons can tunnel. And that's another specific feature of the superconducting state. But this the feature is that for a single electron to tunnel, you need to break up a Cooper pair, and that costs an extra energy, which is called the superconducting gap, and which is denoted by capital delta. So what it results in is the following set of pictures where the even parabolas are where they were, but the odd parabolas with the odd charges, where you have a non-paired electron, they have an extra energy contribution delta. They are higher by this amount delta. Depending on the value of the delta, you can have different situations on the left and on the right picture. If delta is not too high, then the lowest energy state is sometimes green, sometimes blue. So blue, green, blue, green. And you will, if you plot the charge as a function of the voltage in the lowest energy state, you get the lower staircase with the different even and odd stairs. If, however, you are deeper in the superconducting state, the superconducting gap is stronger, then you could have the situation on the right where odd parabolas play no role at all. They are always higher than some of the even parabolas. So in this case, the lowest energy state is always the even charge state. So it switches between 0, then 2e, 4e, and integer number of Cooper pairs. And the Coulomb staircase looks like that. We see it below here. It has these steps which are twice as large as in the normal state. So all these, of course, is easy to understand, but also has been verified experimentally at the early stage of this field. And one of the pictures from the Sackler group, I guess, is shown in the lower right corner of these three possibilities of different Coulomb staircases. Now, so far we have discussed only the charge and energy, and no possibility, in fact, for change of the charge has been included in our energy. If you want to describe the quantum dynamics, we need to take the possibility to change the charge into account. This is the Josephson effect, at which we mentioned. If we take that into account and allow the charge to change, then instead of the crossing parabolas, we would have the anti-crossing situation, as you see in the picture. For instance, initially, if you look at this blue circle here in the picture, initially, without the Josephson effect, we had two parabolas crossing here. If we now zoom in, and it's enough to consider only what happens inside this blue circle, the lowest energy states. If we keep our voltage close to this point, we have all the energy scales, temperature, frequency, low enough, we basically have a two-level system, and the spectrum of the system is shown on this picture to the right. We have what is called the level anti-crossing in quantum mechanics. This is basically a two-level system, which can serve as a qubit, in fact. If you look at this Hamiltonian, which is shown by this 2x2 matrix at the bottom, in the charge basis. Then the diagonal terms give us the charging energy when there is the different charging energy for the two states. The difference is zero. The degenerate, the charging energies are degenerate in the middle of the picture at the degeneracy voltage, and it changes with the deviation of the voltage from this point. And at the same time, the off-diagonal term describe the Josephson effect, the possibility to change the charge. This is the Josephson energy, right? So effectively, if we discuss this in terms of the Pauli matrices, we see that the diagonal terms give us the Z magnetic component of the magnetic or pseudomagnetic field, and the off-diagonal Josephson term is nothing but the pseudomagnetic field in the X direction. That's in fact exactly how we discussed it at the beginning of the lecture. So it allows us to perform quantum computation using this device. This is the charge qubit. And you might think that you don't have enough control here. You can control with your voltage only the diagonal terms of this Hamiltonian, of this matrix. But in fact, first of all, it is already sufficient, as one can see, for quantum computations. You don't have to have full control. And moreover, you can achieve the full control. And that's, as it is shown here, by replacing in our system a single Josephson junction by two junctions in parallel. And in this case, the system, as we know from the theory of superconductivity, you can easily understand it, in fact, by looking at two parallel Josephson junctions, that they can be thought of as a single Josephson junction. This construction is also called the DC squid. A single Josephson junction with the effective Josephson energy, which is a function of the magnetic field applied, which you can apply inside the superconducting loop. So in effect, anyway, then you can effectively have a controlled Josephson energy. And if you look at the 2x2 matrix at the bottom, both diagonal and off-diagonal terms are controlled now, can be switched on and off independently. You have full control and possibilities to perform all single qubit rotations. Very good. So this shows how you can, this shows the status of the ground state of the system, which is sometimes charge 0 state, sometimes charge 2e state, and sometimes a superposition of the two. But I want to, what I want to, in fact, to mention now rather is the first experimental demonstration of the, if you want, a quantum logic gate of the operation of the system. Which was shown by the group NEC in Japan more than 20 years ago, so the first operational superconducting qubit. So this is the charge qubit roughly of the type which we have just discussed. I don't want to go into much detail. The idea of this experiment is the following, shown in this picture. This is the spectrum of our system. And the idea is that you start away from the degeneracy point. Your system is a well-defined charge state denoted by charge 0 here. Then for a short time, you switch your system, you switch the voltage so that your system is switched to the degeneracy point, keep it there for a finite time and switch it back and measure the charge. To understand what happens here, we can discuss it in the spin language. The experiment looks, in this language, looks like that. You start from the system with some magnetic field, in this case in the Z direction, and the spin along the field. Of course, it has relaxed to it after a long while. Then you quickly switch your field to some other direction, in this case to the orthogonal direction, so that the spin doesn't have the time to switch together with the field. What happens then, we know, we have the precession of the spin around the direction of the field B. This is shown in the rightmost picture. This precession takes place, and then if you interrupt it after a certain while, after some time delta t, and measure the Z component of the spin, of course, the value of the spin would be an oscillator function of the time span. And this is exactly what has been done here. And you see in the left bottom picture the oscillations of the charge as a function of this time. And there are mock pictures here, but that's the basic one. So it shows the quantum coherent oscillations, so the quantum operation, if you wish. That's the basic single qubit operation demonstrated in this system. Of course, this has been extended. I just want to flash a picture of a couple qubits, actually a picture also from the same group, which were later using just the capacitive coupling of the islands of two qubits. 2-qubit operations have been demonstrated and coherent oscillations in a 2-qubit system. In 2 qubits, there are 4 levels, which can be controlled by applied voltages here. And 4 levels means more energy differences, more frequencies, more possible frequencies, and all of them have been observed in this experiment. Very good. So this was a very brief introduction of a charge, the basic charge qubit and its possible operation and control. I don't know if you have any questions at this point. Now I wanted to discuss very briefly another approach, the opposite approach, where you use mostly not the charge, but the phase degree of freedom. So please tell me if any questions, or if you have any questions, or if any questions appear in the chart.
There are no questions in the chat at the moment, so we have a few more minutes to go through the phase qubits.
Right. So let me just not really go through that, but tell you that we can also use the opposite limit. We saw how we could discuss the situation where the energy scale, the major energy scale, was the charging energy shown E squared over 2c, which was much larger than the Josephson energy, which we had in mind. The Josephson effect was a small perturbation. But the typical situation, at least many years ago, was the opposite one, where the major contribution to the energy, the Josephson energy, it's often referred to as a classical junction. In this case, you can describe your system using the phase degree of freedom. And the simplest system is just a current biased Josephson junction shown in the picture. In the so-called RCSG model, resistively and capacitively junction model, you can think of a Josephson junction as it is shown in the rightmost picture, as a parallel connection of an ideal junction, a resistor, which describes the dissipative effects. Yeah, we have discussed the dynamics of the phase. So in this case, in the classical limit, the dynamics of the phase is described by this equation. You can call it the Josephson equation, which basically tells us that this is the current conservation. Total current fed externally into the system on the right-hand side is a sum of 3 contributions corresponding to the J, C, and R, to the Josephson junction, the resistor, and the capacitance. This is the Josephson current, the rightmost term on the left-hand side. This is the ohmic term. And this first term is basically the displacement current corresponding to the current through the capacitor. Now, if we neglect the dissipative effects at the first place, as a first approximation, we have a system which can be described by some potential energy in this case, and we can discuss this system also quantum mechanically, as I'm sure you have discussed yesterday. In this case, the potential energy is given by the second and the third term, the phase-dependent terms in the pink frame. Here, so the potential energy is a combination of the Josephson energy, the cosine, and the tilted term due to the external magnetic field. So this is the tilted cosine potential is often referred to as the washboard potential. Now, the first term here is physically is a charging energy, but because the charge and the phase are canonically conjugate variables, the charge here is basically the analog. If the phase is of an analog of coordinate, the charge is an analog of the momentum. They have the same commutation relations. And then the first term can be thought of as a standard expression for the kinetic energy. So basically, the physics of the system is a physics of a particle in this potential, in the tilted washboard potential. And you can discuss various situations. In particular, if you consider a similar system, if you have a superconducting loop in the bottom, interrupted by a Josephson junction and biased by a magnetic flux, the so-called RF squeeze,
Then you have a similar situation, but in addition to the cosine potential, you now have the inductive energy, the energy of the effective inductance of this loop, which is quadratic. Under in a certain parameter range, the combination of the cosine and parabola gives you a double well potential at the bottom, as it is shown in the bottom right picture. And the levels in the left and the right bottom can be used as two levels of the qubits. This is basically the simplest example of the flux qubit. In fact, it turned out that direct realization in this geometry is complicated. It was realized there, but later. But the first demonstration was achieved in a slightly more complicated system with 3 junctions in a small loop, which was done by Hans Moe and co-workers in Delft in the Netherlands. It is a similar system. I don't think I have to go into more detail and don't have time to do that. But in this case, there are 2 independent degrees of freedom, 2 phases. And as a function of those 2 phases, the potential landscape in certain conditions looks like that in the picture. And you have 2 shallow minima, which correspond to which you can think of as 2 states of your qubit. And then you can control the dynamics of your system by controlling the depth of the minima, and the possibility to tunnel between the minima is controlled by the height of the barrier, which is also under control. So this is the basic idea of what is called the Josephson flux qubit. And also basic quantum logic operations on physics terms. Quantum coherent oscillations of the system were demonstrated at that stage. And this is shown in this picture. I don't think I want to go into more detail of this system anyway, and I just wanted to say a few more words about, well, a couple of words about each, about the quantum measurement and decoherence, if I still have a couple of minutes.
You have 2 or 3 minutes, but I think that's not enough to cover the topic of decoherence.
I don't want to cover it, no. I just wanted, yeah, well, let me just indeed mention. Well, perhaps I'll mention the concept of quantum measurement, which we need to be able to perform. We know it from quantum mechanics. We know that it's a situation when we couple our qubit or spin to some quantum detector, and then you randomly get one of the 2 results, in this case, the result 0, 1, and at the same time, we collapse the state of the qubit to the state 0, 1, and that happens randomly with the probabilities given by quantum mechanics, A squared and B squared. What's interesting and important to realize is that this process can be described fully within the framework of the Schrödinger equation. You don't need to infer any collapse postulates. It's not a postulate, it's a consequence of the Schrödinger equation. What I want to mention at this stage, though, only is that the quantum measurement, which can be realized in many different ways, and my colleagues will discuss some examples later on in this school, it's often characterized by the so-called fidelity of the measurement. I just don't want to mention this property. What does it tell us? Basically, it tells us how reliably the measurement works. The question which we need to ask is, what happens if we know that our system is initially in the state 0, or know that it's in the state 1? How reliably we would get the result which corresponds to the state? In this picture, it shows that with the probability of 99%, this happens, but with the probability of 1%, our detector fails. So in this case, the fidelity of the device can be characterized by this number, 99%, but of course, it depends on our device. And this number doesn't have to be the same for the upper and the lower lines. These are, in principle, 2 independent characteristics of our device. Very good. So I think I'll then stop at this point. Since my time is up, I tried to briefly describe the basics of the field of quantum computation and how they feature in basic superconducting, in the case of the basic superconducting qubits.
Okay, thank you very much for the nice lecture.